So first we can take a look at like the subtasks and stuff. This problem one has subtasks, some minimal subtasks. Um, yeah, there's this case that's test 2, and then there's test 3 to 5. Yeah, so if you solve both of these cases, it's roughly like one fourth. Yeah, it's a little less than 1/4. Yeah. And then it's around 1/5 if you solve the first one. Yeah, and then there's the third problem. Yeah, I guess the third problem has more test cases. But yeah, let's go over the problems in order. Yeah, so the first problem is you're given some numbers m and k, and you need to try to construct n numbers where their sum is equal to m, and the XORs of their pop counts is equal to k, right? So pop count is the number of ones in the binary representation. Yeah. Yeah, so some examples here. Yeah, so m equals 2. This is just equal to 2, which has pop count 1. So yeah, so you can do 2, 0, or you can just do an array of size 1, which is 2. Yeah, and cases like m equals 10, k equals 5, you can show it's not possible. Yeah, so let's look at how to do each subtask. Yeah, so for the first subtask, you have m up to 8 and k up to 8. Yeah, so you can kind of brute force, right? So you can try, yeah, so you can try like, yeah, so numbers that sum is equal to 8. You can try all the different combinations of numbers that sum up to 8. Yeah, uh, yeah, and something like this should work. Yeah, I guess another related way is you can do like, you can do a DP where the one of the states is the sum, and then the other state is the XOR pop count. So this will have size 8, and then this will have size 8, up to 8, and you can just pre-compute this, and that's more than enough to solve this first subtask. So let's look at the second subtask, where m is at least 2 to the k, right? So we want the pop count to equal k, right? And a simple example of a number where the pop count is equal to k is where you have k once, right? So there's k once. So this number here is equal to 2 to the k minus 1, right? And here our guarantee is that m is equal to m is strictly greater than 2 to the k, right? Yeah, so we can consider what m is with respect to this number, right? So if m is equal to 2 to the k minus 1 plus, yeah, so you'll have like something of this form where m is equal to 2 to the k minus 1 plus x, which is guaranteed by the subtask. Yeah, and if x is even, then this is pretty solvable, right? The idea is that if you consider x over 2 and x over 2, like you can divide it in half, and these have this, they have equal pop counts, right? So the pop count of x over 2 XOR the pop count of x over 2 is going to be 0, 0, right? Yeah, so then in the case where x is even, you can just have 2 to the k minus 1, and then x over 2, and then x over 2, right? And the other case is where x is odd, right? So here, the subtask tells us that m is strictly greater than 2 to the k, right? So it's of the form 2 to the k minus 1 plus x, and we also have x is greater than equal to 3, right? And yeah, so maybe like we can try to add some even number, and then maybe some odd number is easy, and it doesn't change the pop count. It ends up being that you can, since x is greater than equal to 3, it's going to be equal to 2 to the k minus 1 plus 3 plus y, where y is even, right? So we know we can split this into y over 2 and y over 2 and contribute 0 to the XOR. It turns out you can also make split this up and contribute 0 to the XOR. You can split this up into 1 and into 2, and right? And pop 1 is equal to pop 2, which is equal to 1, right? So then these XOR, the XOR sum of this is equal to 0, right? So in the case where X is odd, yeah, then you have you can split it up into 2 to the K minus 1, and then you can split it up into yeah, you can split it up to y over 2, and then there's this 3 over here, which you can split into 1 and 2, right? Yeah, so if m is greater than 2 to the k, yeah, so we can do this. If x is odd, then we can split into 5 numbers. If x is even, we can split into 3 numbers, right? So now let's consider solving the full task, right? Yeah, so a case where the answer is yes, I wrote this down. Yeah, it's equal to a case where m is equal to 6. Yeah, yeah. So a case where m is less than or equal to 2 to the k, where there's a solution, is m is equal to 6 and k is equal to 3, right? So in this case, we can't use the same approach, because you put 3 ones next to each other, it's going to be 7, right? So we need to try to do something different. It turns out you can this is equal to yeah, this equal to 3 plus 1 plus 1 plus 1. Yeah, and then the pop count of this is 3. Sorry, pop count of this is 2, and then this is 1, and then this is 1, and then this is 1. So they have XOR 3, right? So one thing we can consider doing, instead of using 2 to the k minus 1, consider the smallest sum we can get and having pop count k. So let's say, consider this kind of thing we're trying to do. So pop count XOR is equal to k, and then we want to minimize the sum. Sum. So if we let s to be the smallest possible sum, then we know for sure that m has to be at least s. So let's consider talk about how s would actually be, right? So in this case, for m equals 6, or just looking at this case, like one candidate where the XOR's pop count is equal to 3 is the 7. But we also have we can consider the binary representation of 3. And we can write this as 2 to the 1 plus 2 to the 0, right? So then this has pop count equal to 3, but we can consider this is equal to 2 and this is equal to 1. So this binary number plus this binary number, right? If we consider this sum, this pop count is equal to 2, and then this pop count is equal to 1. So the XOR of the pop counts is equal to 3, and the sum is equal to 3 plus 1, which is equal to 4, right? So for k equals 3, the minimum possible sum we can get is 4, right? We can consider another example of k, right? So we can let k have this kind of binary representation. So this is equal to 2 to the 5 plus 2 squared plus 2 to the 0, right? Yeah, 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 okay, yeah, um, yeah, yeah, okay, yeah, right. So then we can, yeah, so one way to have pop count equal to k is just we make everything equal to 1. But instead, what we can do is, yeah, just making sure I got this. Yeah. So you can consider a number with 2 to the 5 ones, and then another number with 2 squared ones, and then another number with 2 to the 0 ones, right? Compare this with a number with 2 to the 5 plus 2 squared plus 2 to the 0 ones, right? So this sum here is definitely going to be smaller, right? Because you have 2 to the 5, this is less than 2 to the 5. And then if you add these, it's going to be less than 2 to the 6. But here we're like, yeah, we're adding these things. So it's going to be like pretty large, right? Uh, Yeah. So yeah, to minimize the sum where the pop count is equal to XOR is equal to K, you the way to minimize this is you can consider the binary representation of K and then powers of 2 and then break them according to the powers of 2, right? Yeah, so cool. So we need to have M is greater than or equal to S, right? And then we can proceed similarly to how we did earlier, right? So if M is at least S plus 2, which is basically what we did in this version, right? Either the difference is even, where we can break the thing into 2 equal parts, or the difference is odd, where we can break it into 3 plus something that's even, right? So the case where M is equal to at least S plus 2, um, we're good here, right? And then another case that's easier is M is equal to S. We're also good here, right? You just output a single number, or we output the construction that gives you the sum S. Yeah. And then for M equals to S plus 1, uh, this is like another case you have to consider, right? This is possible whenever in the sum for S, it contains a 1, right? So S equals 1 plus, maybe it's equal to 1 plus 4 plus some other things. We can just change this to a 2. Um, and it doesn't change the pop counts, right? Because you're just changing the binary from 0, 1 to 1, 0, right? So the pop count XOR doesn't change, but the sum increases by 1. Yeah, so this is possible in the case where M is equal to S plus 1. It's possible whenever S has a 1 and a 1 term in its sum. Yeah. So that's the solution for this problem. I guess I'll just summarize. Yeah. So yeah, so considering subtask 2 is very helpful in my opinion, to be able to solve the problem, right? Yeah, because you can express it as 2 to the K minus 1 plus X. And there's some cases to do that. And then for the final subtask, we just want to consider how can we get pop count XOR equal to K with a smaller sum. And you can do that by breaking K into powers of 2. Yeah, so that's the solution for the first problem. Any questions before we move on to the second? Oops, sorry.